Hello everyone, welcome to day 14 of 21 days of machine learning with Code Warriors. Now, today's session is all about theoretical concept regarding kernel in support vector machine, what it is, how it works, and like that. So, let's get started. The first thing that you need to understand is there are different types of kernels available for support vector machine. And out of them, three of the most popular SVM kernels are here displayed in this scene. The first one is linear kernel, which split the linearly separable data by a linear hyperplane. Second is our polynomial kernel, which is also referred as polykernel. This kernel function works kind of like the polynomial regression, where it converts the input into polyform and then apply the function on it. The third one is RBF, that is radial basis function. Now, it is also one of the most popular kernel for non-linearly separable data, and sklearn uses RBF kernel by default. I mean, if you don't specify any kernel on creating an object of it, it will set it to RBF by default. Now, the first thing that you need to understand is what is hyperplane and what is kernel. I mean, I told you about hyperplane and kernel in regression, where it only have to fit on data by passing through them, but here in classification it is little different and it is little complex, so that's why we weren't able to conclude it in single session. So then this session is all about the kernel and its hyperplane. Alright, so first we are going to understand is a hyperplane. Hyperplane is a dimensional subspace used to create so that we will be able to split both the categories from each other for classification problems. It is always n-1 dimensional subspace for a n-dimensional space. What does it mean? I mean, yesterday in the video I show you that for 2D visualization it works as a line, which is a 1D, and for 3D visualization it works as a plane, which is 2D. So it's always n-1 dimension compared to the dimension in which it is used. Right? The concept of hyperplane is just similar as in support vector regression, that it needs to fit on data, but for classification it needs to fit in such a way that it gave a clear margin between both the categories, and for the optimization it tries to fit in such a way that it gives margin as maximum as possible. But the learning of a hyperplane in support vector machine is carried out by the function which is referred as kernel. Now, kernel is just an algebraic function that is used to find the optimal hyperplane. We are going to understand the concept of kernel, and also using that concept we are going to understand how it used to classify the categories which are non-linearly separable data. Alright, so let's see how it works. Now let's try to understand with the basic by understanding the 1D concept. So step 1, as you can see in this image, the data points are plotted in a 1 dimensional subspace. Alright, you can see that red points and green points are here, but what kernel does is it applies a function on it, and we are going to understand it by implementing a basic function of ourselves. So let's try to apply a function in which we decrease the value of x1 in such a way that the collection of class in the middle will come near to the 0. So just for the sake of an example, let's think of it like subtracting the value of x with 5. It will fit like this, where the red points here goes in the negative side from 0, and the green data cluster or green data points come near to the 0, as like here. Alright, and then it applies a function on it, and for the simplicity of this example, let's think of it like applying an x square function. So what it's going to do is it's going to first increase the dimensionality. So first it was a 1D implementation, so increasing its dimensionality will convert it into a 2D graph. So here, after applying x square, it will look something like this, as you can see, right? And here our value of x was replaced by x minus 5. So in this function it's going to apply x minus 5 and whole square. So the function will look like this. So after that, all the data points on the x-axis are going to get projected on this curvy line or I mean on this function. So it will look like this, where red points are here, these red points are here, and these green points are here. They are just simply projecting themselves on this curve like this, and this one will be there, this one will go there, this one will go there, and like that. All right. And then it tries to find a hyperplane for splitting both the categories like this. As you can see here, this dashed line will split both the categories, and all the data points of the red category will be on the upper side of this hyperplane, and all the data points of green category will go below the hyperplane, right? And you can see that this line will become the optimal hyperplane for this scenario. And that's how the function of kernel work, where it applies a algebraic function based on data and its relation, and then try to find a optimal hyperplane which will split both the categories, or I mean all the categories from each other. And to understand it, let's try to understand it by implementing it in 2D. So let's think that the example before was in 1D. Let's try to understand it in a 2D space. So here, let's say these are the data points in the 2D space. Now first it's going to do is it's going to increment, or it's going to increase the dimensionality. So it will become 3D from 2D, like here. So it will, let's say it created, the function created a new dimensionality z, and it applies a function, and let's think of it like the previous function was kind of like curvy in concave, and this function will be kind of inverse of it, where it goes like this, and then all the data points will be projected on that, right? And in this way they both the categories will split from each other, and then it will try to find an optimal hyperplane which will be able to split both the categories. Or after splitting the dataset or categories from each other, it converts back or projected back to its original state, which is 2D, and then the hyperplane will kind of look like this, right? And in this way it will be able to categorize or classify both the type of data points from each other. In this way, our model uses a function referred also named as kernel in such a way that it will increase the dimensionality of our space first, and then try to find the optimal hyperplane so that it will be able to classify both all the types of data points, and then it converts them back to its original state. Now you can think like, I mean, increasing a dimensionality and also converting it back, it's kind of complex and it's kind of intense. Alright, so it first increase the complexity, and second it also increase the computational power. I mean, computing these things from function for all the data points will be, I mean, more complex than the regular algorithms. Alright, that's how a model can implement a function to increase the dimensionality first, project the data points, and then find an optimal hyperplane to classify all the categories. And that's how it works for non-linearly separable data. But those the functions that we understand before are just the basic functions that we can think of. But for the more complex data, these functions are not going to work all the time. And that's why there are different types of kernel already available that I told you before, which were linear, poly, RBF, and Gaussian, and like that. So that's are the different types of kernel that can be used. And let's try to understand one of the kernel for here. In this example we are going to understand an RBF kernel, that is radial basis function. Alright, I mean, you can also try to understand other kernels than this by checking out the documentation of sklearn. Also in trying to learn about different kernels over the internet, you can search about them and try to understand how they actually works. And here in this example we are just going to understand this RBF, and you can see this equation is for the radial basis function, where k is referred as kernel. Here x are referred as for the data points, and can be applied for each data points available for our data set, and L is referred for the landmark. Landmark means kind of like a center point, or just the point for the function from where the function starts to grow. Alright, for as you can see in this image, the first image, this is the radial basis function looks like in a 3D visualization. And if you try to plot the center of this radial function, you will see a red point here on this plane, and that is referred as our landmark. Alright, and it's stated here in the equation is L of I, because as the dataset goes more complex and complex, it's not always possible that your dataset only contains one landmark. There will be multiple, and our model automatically tries to find them on its own as they learn from the data. So we don't have to worry about the landmark points and like that. I mean, this looks a little bit complex right now, but next in the next slide we are going to understand it with an example, so it will look a little better there. So let's try to understand the equation first. Let's say here we have a red point, all right? So x minus L will give us a distance between them, all right? So here the distance between the landmark and this data point is more, all right? So converting it square will be a very huge number. Just imagine it, it will be a very huge number. And just the and don't worry about the sigma here, just think of it, it will be a very huge number. So the power of e will be a very huge negative number, so the value it's going to return will be very less. And that means the elevation from this, or I mean the projection from this data point will be very less. And if the data point is nearer to our landmark, the distance between them will be very low. And when the distance between them will very low, the value here, or I mean the rate here, will be less as possible. So means the power for this exponential will be less negative. I mean, if it's -4, it will be less negative compared to a -20. Alright, so here the value will be less negative, so the value exponential is going to return will be more positive compared to the previous one, I mean previous case of this red cross. So the elevation will be more, and that's why it's going to project much more higher compared to this data point. For let's say here in this example, it's just think of it like exam equation, and the first thing it's going to find is a landmark. Landmark is the center of this example, and the data points which are near to it will have more elevation toward them, so they will be projected much more higher. Alright, and similarly the data points that are far away will be projected much more lower compared to the nearer points. And in this way the model can control the elevation of these data points from each other, and it will try to find out the optimal elevation for all the green data points and the red data points. And in this way it's going to project all these green points above, and it's going to let all the red data points remain on the plane, and then it will find out a hyperplane to split both the data points from each other. And here now, to understand what is sigma, the sigma is a parameter that controls the thickness of this landmark. All right, if we increase the sigma, it also increase the it also let more data points get projected on it, and if we decrease the sigma, it's going to get less data points get projected on the this elevation. And that's how our model controls the landmark and the value of sigma to control how numbers of data points are going to get projected on it. And it also controls the position of landmark, so that it will be able to cover or project most data points from this non-linear separable data example. And in this way it will be able to find an optimal hyperplane for this. Alright, and that's how it works. Now you may think a more complex example like this here. So the red data points are like, and in this the kernel will mount the kernel with one landmark is not going to work. And I told you before that our model, or I mean the model itself, controls the kernel based on the relation of data, and the model will be able to find out that it requires two landmark here, and that's why it in the equation it represents L of I here, right? To control multiple number of landmark points for our data set. So in this way it will be able to project two our landmark points for our data set, and it's going to project them in the same way as before by elevation, and then after the hyperplane we will obtain a non-linear hyperplane like this. And that's how a kernel works. That was all about our kernel and an example of RBF kernel, like how it works and its equation. And there are a lot of different type of kernel already available, like polylinear, and there are also pre-computed others. You can try to check out the documentation for them. And in yesterday's session, I told you about the code where you put a hyperparameter kernel and pass a value where it was RBF. You can try to play around on the data by changing its value and see how it works and how it's working. All right, that was all about our today's session. You will get a link to our blog in the description, and there you will be able to find different resources to learn from there. Check it out if you want to have a better understanding of it. So that's it for our today's session. Hope you like it. Enjoy. Keep learning.